Cool. Mark. There we go. All right, so let's talk about networking and communicating with computers and stuff, right? So, I don't know, this is the way that my brain works, but I'm going to start from like first principles almost, right? So, so like, you know, you've seen this diagram, right? No, except I'm going to draw an LED, which looks like a mushroom. And and there's a battery in here, and a switch. Right? So using that, oh, you totally can't see that on the
You can
video.
use the red, but it's very difficult to erase.
All right, you gonna throw me the red?
Sure.
But
It works.
Anyway.
There's a purple down here.
Purple's probably best.
Nah.
This you can't erase. The purple you probably can.
All right, toss me a purple there.
Teamwork, relay, circuit, right?
Ooh,
Yeah.
Yeah.
So
So
if you didn't know Yale's an electrical engineer.
You can see it a little bit.
mechanical.
Mechanical, even better.
Yeah. So now we've got this little LED here. It's cool. It lights up. So pretend like this end of the room or this end of the circuit happens to be like in this room, and that end of the circuit happens to be over there on the other end of the building. Well, I could like tap you Morse code like on the other side of the building. We can communicate in some way, right? Pretend if that were like a buzzer, right? And then we made a circuit where like there's a buzzer in this room and there's also a buzzer in my room, and now we each have a switch. And like as long as we decide like, oh, you know, when I'm talking, you don't talk, and when you're talking, you know, we share this circuit, and like I'll talk to you, and then you'll talk to me. You know, you can communicate that way, right? And so going back to like Alexander Graham Bell, the telephone, right, which was basically just like one circuit powered, and like you would talk on this end, and it would vibrate you would talk into a microphone, and it would vibrate the speaker on the other end of the thing, right? And so, you know, beginnings of communication across like a wire, right? You want to toss me an eraser too?
It's all the way back there.
So I'm going to start from there. So so that was like the first communicating across a wire.
It erases.
Yeah. And then we said, well, that's not very efficient. We're not going to string wire from each person's house to every other person's house. So we'll have a phone, and we'll connect to this thing here. And then we'll like run from there to another thing, and then we'll go to, and these are like houses out here. I'm really using the whiteboard so that I can draw crappy houses.
That's perfect.
That's really what my goal was. So this thing, call it a router or something like that. In the old like analog telephone world, you know, maybe this line here, maybe a bunch of houses were on it. They called it a party line, right? And so as long as you and your neighbor weren't on the phone at the same time, you could pretend like you owned that line. But if your neighbor picked up the phone, they could hear you as well, right? So they're all just kind of strung together. They're all talking at the same time. But it goes to this router, and between this router and that router, maybe we have 1,000 conversations going on. So how do you actually, so here, connected to your phone, you've got a hard wire, and then you go through this router thing, and we need to share this one line between these multiple routers, right? And maybe it has 1,000 cables in it, but I don't think it does. So they started like time slicing. So they would say, conversation one gets like 1 millisecond or like 10 milliseconds, and then the next conversation gets 10 milliseconds. And as long as both ends understand like what the timing, they agree on timing, now you can multiplex that line, right? You can have a bunch of conversations going over at the same time. So that's cool, but that also has a limit of like, well, we've got maybe 1,000 conversations going across this line, but you still have to have like a direct route, right? So then, say we start adding in some more routers, and we're like, we want some redundancy in here, and so now we've got like a network of routers, and you can, you can set up a route, like a hard path, and as long as all the routers agree, then you can still like multiplex and talk over it. But somebody at some point, right around the time of the ARPANET or whatever they called that, they thought, but what if instead of agreeing on the route ahead of time, like what if we don't agree that phone number, 505 whatever is talking to phone number 444 blah blah blah, whatever. We don't have to agree on that ahead of time. We can just give this thing an address, and then we'll give this other thing an address, and then every chunk of data, right? So before it was like analog signal, and then it became digital. So how about each chunk we'll just attach an IP to it, right? So we'll say, this computer can talk to that computer because this computer knows that it's talking to, 127 dot blah 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 blah, and so we'll just attach that to every packet, and then the packet, like packet 1 can go this route and packet 2 can go this route, and it doesn't really matter. But there's a problem with that, because so packet 1 went through 3 routers, which is going to take a little more time than packet 2 going through only 2 routers. And so your conversation, your communication between computers, packet 2 may arrive before packet 1, and that's a little confusing because you don't know what order they should go in, right? So they invent UDP, which is the datagram protocol, and user datagram protocol, and TCP. And TCP allows you to kind of pretend like you have a hard line direct path between your 2 endpoints, and say, my message is going to arrive in order, and all the pieces are going to arrive, and we're just going to pretend like they're just hardwired together, even though in the middle it's going like crazy willy-nilly all over the place. But by the time it gets to your end, you've got the whole message, and it's in order, and you can pretend like that is how it happened, even though it didn't. So now let's talk about computers. Computers are cool. Yeah. So your computer understands TCP as well as all the routers in between understand TCP. So on our one computer here, this marker is dying on me.
No.
That's really good. I'm gonna switch into red, man.
Oh no.
Doing it.
Risk it.
Oh, this isn't a dry erase marker.
No, it's a regular erase marker. A wet erase marker.
Ooh, it's so bright though. So this is our computer.
I'll grab it.
Oh yeah. So that's our computer. We've got a line coming into it.
Is that a CRT?
That's a monitor. That's not a.
Yeah, that's a monitor, but
Oh.
it's a Mac. It's an iMac.
Oh wow!
It's all integrated.
I've never seen that resolution.
Jumped
Yeah.
forward a long time.
So we've got our little packets floating across this wire. Yeah. So those are coming in, and they're addressed to my computer, and my computer can receive those and reorder them, put them in the right order for me, and then my OS steps into the picture and says, roll back for a second. we've got an application, and the application says, I'm interested in all TCP packets that come into the port of 5000, right? So port 5000, that's where I expect people to talk to me. Tell me about that. When somebody sends me a message on port 5000, tell me when that happens, and then I will take care of those packets, right? And so the original way to do that was blocking I/O, which your application would sit there and it would say receive. Let's call it receive, because I don't know what it's actually called. Receive data. Receive data. Sure. Data. So it would sit there in a loop, and it would receive data, and then it would process the data, and then loop back, sit there, receive data, process data, right? So this loop, the only problem with it is that every time you hit this receive data, if there's no data available to read, it just sits there. So it's blocking. So that is an issue when you want to fully use the resources of your computer, right? So in Linux, there's a thing called epoll, which is a system call, which is the equivalent of receive data, except with a different API. So epoll, the difference there is that you register with the OS. You say, I'm interested in data coming in on port 5000. You call me when someone.
So is it like the publisher subscriber kind of schema?
Kind
Design pattern, I guess?
So with epoll, there is still a loop, and there is still a blocking call. Mm-hmm. So it's a little different, but what you can tell it is, yes. So you have to pull the results,
sure,
right?
That's fair.
And it gives you data from those sockets. But the setup beforehand is you have to tell it which sockets you're interested in. So I think the original, well, this is where I get hazy on things, right? So I've used it from a high level from Rust, not like the super low level from C. So now we can actually get into some nice computer-based things.
Are you gonna listen to port 666? Play some Doom?
No, 8080.
Some original Doom?
Yeah. So, some things I thought were neat. As I was, yep.
It's got to pull for a second.
Come on.
Next one, hopefully, computer 2. There you go.
Yeah. As I was researching about networking and such, I happened to find this on Twitter. This is
the internet.
Somebody's grandpa took a picture of this diagram, and it was the entire internet as of May 1973.
Got Harvard,
Yeah.
you got Carnegie.
You've got schools on there. You've got Harvard,
the entire state of Illinois.
Aberdeen. Yep, there's Illinois. There's Utah.
Hawaii's the odd man out on the left.
What's that?
Yeah.
And Hawaii's over here. Yeah, I guess maybe that's an undersea cable.
Well, so this just proves that the world is flat, if I understand correctly.
Yeah, there's no curvature there.
Yes.
Nope, there is no curvature.
Well, Hawaii is some form of squiggly away, but still flat.
Exactly.
Yeah. So when the TCP protocol was invented, this is what the internet looked like
Wow.
around this time, right? And another cool thing I found was this girl made a series of drawings that is what happens when you download a cat picture.
Hey.
and it's super simplified, but it's pretty awesome. Yeah. So definitely something to check out. Also gives you some cool like traceroute. Traceroute is a little console app that you can call. You can say traceroute to google.com and it'll tell you all the intermediate servers it went through to get there. So pretty cool stuff. So let's look at some Rust.
What's the Wi-Fi real quick?
Oh,
I'll grab you the sheet.
It's the SGA2.1.
I was pretty sure it had perhaps the password.
yeah, the password did change. So we'll start here with, so the two kind of foundations for all the,
Thanks.
well, I guess three foundations for all of the asynchronous networking and other things you might want to do asynchronously. There's a crate called Futures, and there's another one called tokio-core. And tokio-core under the hood uses another thing called MIO, or MIO, which is Metal IO, and that's just an abstraction over the top of. So on Linux it's ePOL, on BSD it's a different API, and on Windows there's an IO completion port or something. So MIO just kind of abstracts over the top of those and provides a the same API on top of all of them. So this is the kind of hello world of asynchronous networking. I wish I could kind of make this go away. View panel? No. Anyway. So, yeah, it's going to be hard to see on the video, but, and here. Can y'all see all right? Or can I reduce the font size a little bit?
See from the back?
Yeah. There. Now it all fits in one screen. Hopefully that's not too bad.
Now they have a harder time seeing.
Well, now it's going to be harder. So let's walk through it, right? So we're going to say that the address we're interested in is localhost 8080. We're going to turn that into a socket address. So at first we have a string that is the port name and number, and then we're going to parse that into a socket address. And so parse is a function that anything that implements the trait from string, you can use parse to get something out of a string, right? Or convert something from a string. Core is part of tokio-core. That is going to be our event loop, right? So we need the event loop to sit there and poll and listen to events, right? So the events are coming from the OS that says there's data available on the port, now you can read. So then we're going to start a TCP listener that listens on that port, and then right. So listener.incoming. So incoming says for each new connection, right? So every time somebody connects to this port on my computer, we're going to do something. So that provides us a stream of clients that are incoming, right? So every new person that comes up, and then we're going to do something with that, and clients just so that incoming there provides us a stream of tuples that the two pieces are the socket and the address of the other person, right? So I know my address. I'm at 127.0.0.1, port 8080. But what is their address, right? And not that I'm going to do anything with that in this example, but we're just going to say, hey, tokio-core IO, write data to that socket. So they've connected to me, and then I'm going to write data back to them, and I'm just going to write a byte stream of hello, right? So then you're going to turn that into a server. So those are the welcomes for each one of those. We're just going to say, yep, okay, and this core.run is where you take your future. So we've got a stream that we've got a stream of incoming things, and then what we're going to do with those incoming things, and we've defined all of that. And now we're going to say this core, right? And core is our event loop. That's going to loop. We're going to say, hey, do this, run these things, right? So start running, and that's gonna loop forever, basically. Yeah. So we can actually.
Do you have a way of stopping it other than killing it?
Killing it.
Okay.
Killing it works.
What are the vertical lines beside the tuples?
So the vertical lines are, so those are closures. So those are like in JavaScript where you would say function whatever without giving it a name.
Okay.
Yeah.
Huh.
So that's just a shorter syntax for doing the same thing, right? So just defining an unnamed function. Yep. All right. So we can run this deal.
Oh, so neon.
Is it? Let's make it bigger.
Nah, I mean, it's about. There you go.
All right. So I cheated, and this is actually built into the Tokio-core. So there's a neat feature in Rust, well, in Cargo, that if you have a file structure of your application, you can add a folder called examples, and any file you put in that examples folder becomes something that you can run just by calling cargo run example, the name of the example, right? So that was the hello. So now I'm listening on that port, right? And so I can go over here and I can say in C, which is a program that just makes a TCP connection and then outputs anything to the console that came from it. And I can do local host and port 8080, which was the port we assigned. And so, not that anyone could see that because it's tiny, but we made the call. We called them on the socket got the connection, wrote hello back to us, right? So very, very simple thing right there. So getting a little more awesome.
Oh, spoilies.
Oh.
Chat RS.
Yeah.
Did you write aim in Rust?
No, I did not.
Oh.
But I will. So this one gets a little more complex here. So we're doing all the same things, right? We're getting our socket, we're turning it into a socket address. But now, so there's our event loop that's going to run our thing. And now we're going to get a handle to that event loop, which is just a pointer to that event loop that we can use later, right? So same thing, we're going to start listening, and then we're going to say incoming, so that's all of our clients. Each client, we're going to take the socket and the address, and that socket we're going to split into two halves. So we've got a reader half and a writer half. Now there's this function that is built into tokio-core that if you just want to take two streams and you want to read from one stream and write to the other stream, then you can use this thing called copy, right? And then that's going to return the amount of data that it wrote. So then we're going to take that, map it to a command to write to the console. So either it wrote bytes or something went wrong and we're just going to blow up. And then this handle. So there's our event loop, and so we're going to say So that copy that we set up, that's gonna do the act of copying, that's actually a future. So it returns as a future that then will, or is it a stream? One or the other.
Huh.
Futures are streams. Streams are futures.
Whoa, very meta.
So
Dr. Strange.
we're going to take this thing that is doing the copying and we're going to spawn that on our event loop too. So we've set up the connection, and then for each connection we're going to add that connection to the event loop as well. So now we're interested not only in any new people, but we're also interested in this this socket that we already set up, right? So that's part of this, why it's asynchronous I/O, because we're going to be looping over, but we're going to say, hey, not only are we interested in
Reading, but also writing.
yeah, well, not only are we interested in new connections, we're also interested in existing connections that we know about, and we can handle all this on a single thread. So, and the problem with threads is that eventually you have a lot of them. So we can run that, and that one is called Echo. Just going to compile for a minute. There it is, it's listening. So now we can do the same command, and we've started up. So now we started a connection, and you can see before, whereas it immediately exited because we had on the server side we had just dropped it. Right now we've set up a connection, and the connection is live, and we are not closing it. So now I can say hello, and it'll echo it right back to me. Yeah. Damn. So pretty cool. And you can see, so we closed our connection over here, and since we closed it, now that connection, and that was the port we were talking from, even though we never assigned it. We were talking from port 39,270, and it said, hey, we wrote a total of 15 bytes to port that other port. Pretty cool. So let's do, I will try and make a good demo of this. It's something I've been working on, and hopefully it all works at the moment. That is questionable.
It's going. This one seems a little bit more complex than the others.
It's doing something. Yes, it's compiling lots of stuff and giving
Lots
me
of
lots
warnings,
of warnings.
But no errors.
Not yet. Hopefully. I haven't compiled it in a while, apparently.
Oh, no!
And blow up. That's great.
You're so close. OID.
Oh, darn, that's part of... Do I have... Hold on. Oh. Oh, good. Git checkout master.
He's hacking. He's hacking the government.
No! Why does it... Oh, wait. Git stash.
Oh, we found the stash. We're supposed to get rid of the stash, you mean?
Yeah, his computer just shuts down.
Yeah. And smoke comes up.
Oh, I feel like it's going to work now. Yes! So,
Whoa.
so I have a Postgres server running on my computer, and and I've built a Postgres proxy that understands Postgres commands, basically. Let's do this. So this server here is my local server, and this is my proxy. So everything that's in my local one should be also within my proxy, because it's just proxying all the data. But the cool thing is that since I'm listening in, oh no, I haven't, this is an old version, darn it. Well, I wish I could show it to you, but I'm not going to sit here and fix my code. But since I'm listening in and I can actually understand the messages that are going between my PG admin here, which is querying what's in the database, and my database itself. So I can listen in on all the queries, and I was printing them all out to the console. So each query that goes across the wire, I was printing them out. Yeah. So, wish I could show you more of that.
It's so cool that you can do it.
Yeah. The code itself is
Also slightly terrifying that you can do it. But
I still haven't figured out how to deal with encryption.
yeah, well, that one's kind of a little tough, right?
Right.
Yeah.
So could you change the TCP to listen for like ICMP,
CMP?
like pings and stuff?
Yeah, you could. Yeah.
Could you do the same with email servers and whatnot?
Yeah, definitely could. You would have to. So the way that ports work is that like TCP port 80 is a different port than UDP port 80, which is a different port than SMTP port 80. So you would have to have an adapter, and I've never written one. Tokio-core provides at least TCP and UDP. It may provide more. I haven't played with that, but you would do the exact same thing, except you would say, I want an SMTP stream instead of a TCP stream.
I was thinking if it could listen for like pings, and you had just a simple small app saying listen for pings, and if you log more than this number and this amount of time, it could essentially be a stop for a ping of death.
Yeah, someone's DOSing you.
Yeah.
Could essentially catch it. I mean, it seems like there's a light enough way puny the WAF runs. So.
Right. Yeah. It's small.
Actually, it's pretty cool though.
So that is what I've been working on, and that is what I've learned about networking.
How many things did you import when you were compiling it down on that? A couple?
How many? Yeah, a couple. Let's see.
A couple now.
So
It seems so many more than that.
so like error chain
Oh, but those
is a library, and it has a
dependencies
dependency, and they have dependencies, and so I depend on this, but that depends on 5 other things.
Sure.
So yeah, which is one of the cool things about Cargo, is that I can just say, hey, error chain, that's what I want to depend on, and it can figure out the dependencies for me.
Oh, that's cool.
Yeah.
Probably wrote this in a previous meeting, but what is Cargo?
Cargo is the build tool. Well, it's the build tool and the package manager, pretty much.
Okay.
So in C# it would be the equivalent of like NuGet manages packages, and MS Build is your build chain. So it replaces both of those with one in a nice kind of integrated. And this file, this cargo toml, is your configuration. And it lists out your dependencies, it lists your package name, version. You can put other information in there as well. So.
I was looking up their repo. I guess they formed a maintenance team, and they're making a version of that, tokio-core,
Uh-huh.
on top of Hyper.
They're moving Hyper to use futures. Are they using tokio-core as well? Yeah, so pretty much the networking story for Rust is going to get really good, and also just async in general. I feel like the core pieces have been built up rather recently, but I mean, yeah, it runs async on minimal resources and lots of nice concurrency guarantees that go with it, just due to the Rust type system. So yeah.
What's the package manager called in Linux?
What's the package manager in Linux?
What's
apt is